Chapter 1. Did JWST just find hints of life on K2-18b? On September 11th, 2023, astronomers released a quiet but groundbreaking announcement from the James Webb Space Telescope team. They had observed something intriguing in the atmosphere of a distant exoplanet named K2-18b. Located about 120 light-years away, orbiting softly around a red dwarf star. This distant world is no ordinary planet. JWST detected clear signatures of two common carbon-containing molecules, methane and carbon dioxide. To see these molecules, astronomers examined the transmission spectrum of K2-18b. Now, what exactly does a transmission spectrum look like? Imagine a foreign planet cruising around its star as it passes directly in front. Some starlight seeps through the planet's extended atmosphere, around its edges, towards us. Molecules in the air absorb specific wavelengths, leaving behind clear marks called absorption lines, a distinct fingerprint revealing exactly what's present. When astronomers looked carefully at K2-18b's cosmic fingerprint, methane and carbon dioxide loudly announced their presence, while another commonly seen molecule, ammonia, was strangely missing or scarce. Methane and carbon dioxide in an exoplanet's air would be exciting enough, but that's not the end of the story. Among the complex web of spectral lines, astronomers identified a faint hint of another molecule, dimethyl sulfide. This molecule, commonly abbreviated as DMS, is rare and fascinating because here on Earth, it's primarily produced by marine phytoplankton, the microscopic plants floating in our oceans. On our blue planet, DMS signifies biological activity, making its possible presence elsewhere incredibly intriguing. Soon after the announcement, astronomers around the world began to sit up straight. So, could there really be something living, swimming perhaps, in the oceanic depths of this alien world? Astronomy enthusiasts buzzed with enthusiasm, dreaming visibly of ocean-covered planets brimming with life forms completely different than anything we have ever imagined. However, as often happens in science, excitement was also tempered by healthy skepticism. Immediately doubts arose. The detection of dimethyl sulfide, many researchers pointed out, was tentative at best. The observed signal was faint and noisy, challenging to distinguish conclusively from stronger signals like methane. This ambiguity, researchers cautioned, might simply be due to random noise or overlapping chemical signatures, making it extremely difficult to pin down dimethyl sulfide conclusively. Indeed, the signal's statistical strength didn't initially meet traditionally rigorous thresholds. Astronomers typically require something called 3 sigma statistical certainty before confidently declaring significant findings. For context, 3 sigma indicates there's less than a 1 in 300 chance of the detection occurring by random chance alone. Such a stringent standard helps shield astronomers and the public from overstating their findings prematurely. This time, the initial observation of dimethyl sulfide fell below that threshold, demanding caution. Many researchers also pointed out another possibility, that DMS could actually be produced through non-biological or abiotic processes. For instance, DMS has been seen in cometary matter, where conditions are unambiguously lifeless. This observation raised a critical but challenging question. How can we truly differentiate a biological signature from an abiotic, purely chemical process when both can create identical chemical fingerprints? This conundrum set off a lively scientific debate, a public clarifying exchange rarely seen in astronomy. Two teams carefully analyzed these same JWST datasets, each offering distinct interpretations. One group cautiously emphasized the anthropocentric bias, urging careful interpretation. They reminded everyone of historical incidents in astronomy when ambiguous claims initially created excitement, but ultimately had to be revised after more precise data. The second team embraced guarded enthusiasm, pushing forcefully against excessive caution, emphasizing that life-driven chemistry might manifest similarly across different planetary systems. This friendly scientific duel unfolded openly through debates, lively scientific conferences, and exchanged publications, reminding us of how real science struggles forward, not by asserting but by testing and counter-testing, debating and re-examining again and again. So let's pause and return briefly to K2-18b itself. What exactly is this elusive world? We know it's intriguingly larger than our Earth, about 2.6 times its radius and weighing roughly 8.6 Earth masses. It journeys around its small, cool red dwarf star every 33 days, far closer than Earth lies from our Sun, yet still placing it in a comfortably cool region, precisely within what astronomers call the habitable zone. This zone is neither too hot nor too cold, ideal for liquid water to exist on the surface. A fundamental ingredient for life as we understand it. The relative proximity of this alien world, at 120 light-years away, makes repeated, more precise observations feasible. Future studies, particularly repeat visits by JWST, could sharpen our blurry picture considerably, potentially transforming today's tentative hints into clear conclusions. Jumping back into the bigger picture, astronomers face a deeper puzzle. What is the true nature of K2-18b's surface beneath this shrouded atmosphere? Two competing theories emerge prominently. According to one model, it may simply be a large gaseous world, much like our own solar system's Neptune. In this scenario, no solid or oceanic surface exists beneath those thick atmospheric layers, reducing hopes for habitability. But another viewpoint suggests a far more tantalizing scenario, that K2-18b is what astronomers now call Hycean, a hybrid world. A Hycean planet combines a deep global ocean full of liquid water beneath a remarkably dense, hydrogen-rich atmosphere. Such a world could provide all essential ingredients necessary for life, from abundant water, protective atmospheric layers, potentially stable conditions for life to thrive in deep oceans warmed gently by internal heat and starlight combined. All these fascinating clues and hypotheses will largely depend on continued detailed observations. Indeed, JWST is set to examine K2-18b once again, this time utilizing the powerful mid-infrared instrument, or MIR-I, aiming for the crucial 3 sigma confirmation threshold. These critical observations, planned for 2025, will either reinforce or dismiss these early signals, and might confirm once and for all whether this mysterious gas, dimethyl sulfide, truly exists around K2-18b, pushing the edges of astrobiology and human curiosity even further. Our preliminary exploration of K2-18b's exciting but complicated results naturally leads us to deeper questions. Exactly what is a Hycean world? Why does the possible discovery of such a place matter so profoundly to science and our search for life? To uncover this, we need to carefully piece together how planet formation, atmospheres, and oceans interplay to possibly nurture life. What would it truly mean if other Hycean worlds sparkle throughout our galaxy? Let's take a closer look. Chapter 2. Inside a Hycean world's steamy ocean skies. In 2021, astronomers introduced us to a whole new type of planet called Hycean worlds. A fresh concept blending two key words, hydrogen and ocean. Picture an entire world shrouded in a thick atmosphere, one rich with hydrogen gas, resting atop deep global oceans. These planets are larger than our Earth, often measuring up to 2.6 times Earth's radius and weighing as much as 10 Earth masses. These worlds hold our curiosity for a critical reason. Their robust hydrogen envelope expands significantly under stellar radiation, ballooning their sizes visibly in the telescopes we point their way. Why is that so helpful? Hydrogen, being a lightweight gas, readily inflates under radiation, providing a more expansive atmospheric canvas. That inflation makes it easier for astronomy's premier tool, the spectroscope, to detect what's in their alien skies. By analyzing atmospheric light signatures, we can spot critical chemical compounds even across vast interstellar distances. But what does living on a Hycean world actually mean? Consider their interior conditions through something scientists call temperature-pressure profiles. On a typical Hycean planet, beneath the murky hydrogen skies, water could exist comfortably in liquid form at pressures between 1 and 10 bars. To put that into perspective, 1 bar is roughly the atmospheric pressure you feel standing at Earth's ocean surface. So at 1 to 10 times Earth's sea level pressure, liquid water could exist abundantly in a relatively stable environment. To imagine this clearly, think about Earth's oceans. Close to our sea surface, life thrives comfortably around 1 bar, where sunlight warms waters easily. Descend 10 meters down. The pressure doubles. Deeper still. Pressure climbs and temperatures stabilize. Yet Earth's ocean remains hospitable. Similarly, Hycean worlds could host oceans warming gently beneath their vast skies, ranging from temperate to near boiling at greater depths, yet potentially habitable throughout significant stretches beneath their cloud cover. But nature often balances on delicate boundaries, and Hycean planets illustrate this clearly with what's called the greenhouse balance problem. Hydrogen atmospheres act as perfect insulators, trapping warmth efficiently. Too thin. The ocean freezes. Too thick. And heat traps endlessly within, turning these oceans into searing cauldrons, unfit for life as we understand it. This elusive sweet spot in atmospheric thickness defines the narrow belt of conditions where life might comfortably flourish. We've seen analogs on our own planet. Billions of years ago, during Earth's Hadean Eon, a time so remote we barely recognize Earth, volcanoes belched hydrogen gas into a shroud that enveloped the young planet, creating a damp, warm atmosphere known colloquially as the Hadean hot tub. Much of Earth's earliest chemistry took shape during these conditions, showing us how potent a hydrogen-rich atmosphere might be for nurturing life's precursors. The skies of these distant worlds are far from clear, though. Hycean planets frequently harbor thick cloud decks filled with complicated photochemical hazes, often forming from ultraviolet radiation, kicking chemical reactions into high gear. Such clouds act like a two-edged sword, potentially blocking spectral signals from underlying molecules while simultaneously creating distinct chemical fingerprints. Analyzing these hazes can, ironically, reveal the chemistry hiding beneath them. Understanding this interplay is crucial for deciphering remote observations of distant worlds. The world we know as K2-18b, astronomers' best current candidate for a Hycean world, offers a fascinating example. Orbiting leisurely in its star's habitable zone, this intriguing planet displays abundant methane and carbon dioxide in its thick atmosphere. Yet ammonia, so common elsewhere, is mysteriously absent. The reason? Scientists believe ammonia, soluble in abundant oceanic waters, disappears efficiently beneath ocean layers, leaving none behind in observable atmospheric signals. This absence isn't just curious, it reveals water's presence beneath the hydrogen haze, supporting the hypothesis of a liquid ocean vast beneath the clouds. How do we confirm and understand these atmospheres further? Here, scientists turn to sophisticated laboratory experiments. carefully replicating Hycean chemical conditions on Earth to grasp the processes that shape their skies. In controlled tests, researchers have mimicked abundant hydrogen atmospheres under artificial ultraviolet starlight, and remarkably, produced dimethyl sulfide, DMS, and carbonyl sulfide, COS, compounds typically linked to biological processes on Earth. These results show us a twist. Chemicals we commonly consider as biosignatures, possible indicators of life, might also arise through natural, non-biological reactions. This understanding sharpens our tools significantly when searching for genuine signs of life beyond our solar system. Today, our exploration of Hycean worlds is just beginning. The complex chemistry seen in laboratory setups helps clarify what these distant cloudy planets might reveal or hide from our telescopes. As we gaze farther into their distant skies, astronomers eagerly refine the tools needed to differentiate between these false biological signals and authentic markers of alien life. From imagining the vast oceans below hydrogen skies to discerning subtle clues hidden in clouds, scientists continue to push the threshold of our understanding. Hycean worlds are a revolutionary concept, compelling astronomers toward new methods of detecting and understanding atmospheres and possible life. As we refine our observational toolkit, these oceans blanketed by hydrogen skies might soon offer precious insights into one of humanity's most pressing questions. Is life common elsewhere, or is it uniquely bound to earthly shores? With that question guiding us, let's move onward, exploring how astronomers and scientists use the broader toolkit available today to capture signals of life far beyond our home planet. Chapter 3. How telescopes sniff alien air for biosignatures. Imagine this scene, a distant star dipping slowly behind the edge of an alien planet, glowing orange and gold, its starlight filtering softly through a hazy distant atmosphere. The gentle shift in colors is subtle, yet profound. It's not merely a sunset billions and billions of kilometers away, it's something far more insightful. Captured and decoded, these fading rays of stellar light become clues, tiny fingerprints of a planet's atmosphere. Scientists study these minuscule fingerprints to uncover one of astronomy's greatest mysteries, extraterrestrial life. But how exactly can this delicate, distant filtering of light tell us anything meaningful about alien atmospheres? Let's begin by stepping through a technique called transmission spectroscopy. Imagine shining a light through a foggy glass. The foggy substance absorbs certain colors of the passing light. Similarly, when a planet passes in front of its star, its atmosphere absorbs precise wavelengths of that star's light. By carefully measuring how the star's spectrum changes before, during, and after the planet passes by, astronomers identify which gases fill its atmosphere. There's also the method called eclipse spectroscopy, but it works in reverse. When a planet disappears behind its star, the starlight briefly stands alone. Subtracting the star's solar performance from the combined star and planet glow leaves the planet's own warmth and any atmospheric warmth revealed. Think of it like listening carefully for a single instrument. When the orchestra pauses, this allows us to detect emissions from the planet itself. Another elegant approach uses direct imaging, quite literally capturing snapshots of planets orbiting other stars. Specialized techniques block the overwhelming brilliance of the star, allowing faint reflectance or emissions from planet surfaces or atmospheres to gradually stand out. Imagine blocking your eyes from the sun by raising your hand to observe a dim object near it clearly. But what exactly are we searching for in these delicate fingerprints of light? One key concept is chemical disequilibrium. Normally, chemistry settles down, a balanced mixture of stable gases reacting slowly or not at all. When astronomers detect gases that shouldn't coexist easily, such as methane and carbon dioxide in unusual proportions, they pay close attention. On Earth, for instance, life vigorously consumes and produces gases, disrupting what might normally be a calm chemical balance. Methane together with oxygen or carbon dioxide could suggest something actively replenishing a gas, potentially something alive. So, what gases raise eyebrows most often in this cosmic hunt? First, oxygen and ozone, O2 and O3, often indicate photosynthetic life like plants or algae. On Earth, their abundance stems largely from biology. Methane and oxygen, the CH4 and O2 combination, is strikingly unusual on a lifeless planet. They're rapidly removed by chemical reactions. Dimethyl sulfide, or DMS, released extensively by Earth's phytoplankton, is another tantalizing signal. Also intriguing are phosphine, a simple yet rare molecule naturally produced by certain microbes here on Earth, and nitrous oxide, laughing gas, commonly generated biologically. Recognizing these chemicals in distant skies hinges upon highly sophisticated instruments, none more exciting right now than those aboard NASA's powerful new James Webb Space Telescope, or JWST. The JWST carries critical instruments optimized for sniffing out biosignatures. First up, the Near-Infrared Spectrograph, or NIR spec, operating from 0.6 to 5.3 micrometers. NIR spec is supremely versatile. Using high-resolution observations, it precisely measures atmospheric compositions. Scientists can pinpoint the delicate absorbance patterns left by chemicals like methane, water vapor, and carbon dioxide. It's like a molecular detective combing carefully through invisible patterns of infrared sunlight slipping through a planet's sky. Then we have the Near-Infrared Imager and Slitless Spectrograph, or NIRESS, ranging from 0.8 to 5.0 micrometers. NIRESS is expertly tuned for time series spectroscopy of transiting planets. It tracks subtle fluctuations in starlight filtered through atmospheres, uncovering details about fingerprints left behind by water and methane. It's like repeatedly watching a movie frame by frame until hidden patterns emerge clearly. And finally, the Mid-Infrared Instrument, or MIRI, operating between 5 to nearly 29 micrometers. MIRI extends JWST's capabilities deeper into infrared. MIRI's specialty is detecting thermal emissions directly from planets, not just what starlight passes through, but what planets radiate themselves. It can identify crucial absorptions from ozone, methane, and carbon dioxide. Additionally, its coronagraphs can block the overwhelming glow of stars, making even faint planetary companions visible, essential for genuinely seeing exoplanets as distinct worlds. Yet even miraculous instruments require caution during interpretation. Take methane detected on a distant planet. Couldn't volcanoes simply release methane? Indeed, geological activity can mimic biology's chemical signatures. Similarly, oxygen-rich atmospheres might also form through photochemistry, where ultraviolet starlight splits water molecules apart, potentially producing false signals of biological activity. Even human industries, as we've seen on Earth, could produce unnatural chemicals like chlorofluorocarbons, fooling distant observers into wondering about technologies. To untangle these possibilities, researchers combine diverse fields, climate modeling, photochemistry, geology, into cross-disciplinary models to reliably distinguish true biological signatures from mere geological or atmospheric reactions. These rigorous methods prevent premature life-related claims. Speaking of cautionary tales, think back to Mars during the late 20th century, the now famous Martian methane saga. In the 1990s, detection of methane in Martian skies triggered excitement. Methane could signify life. So many eagerly wanted this discovery to be real. However, critics argued the instruments weren't reliable. Maybe the detection was simply a measurement glitch? Subsequently, in the early 2000s, orbiters like ESA's Mars Express seemingly confirmed methane, measuring around 10 parts per billion annually, with higher seasonal spikes. Yet investigators later pointed out possible instrumental errors again, and today, methane's Martian presence remains contentious. The lesson: extraordinary discoveries demand extraordinary evidence, careful validation before making extraordinary claims. Learning from Mars, future missions aim at meticulous precision for exoplanet biosignature hunts. ESA's upcoming aerial mission will characterize exoplanet atmospheres, distinguishing genuine biosignatures from mimics with unprecedented reliability. Further ahead, NASA's ambitious Habitable Worlds Observatory will sharpen direct imaging techniques immensely, perhaps directly observing Earth-like planets' atmospheres and surfaces, hunting explicitly for life signs. Ground-based, extremely large telescopes, or ELTs, like the European ELT currently under construction, will complement these space-based missions. With enormous mirrors, these telescopes will gather vast amounts of starlight, carefully dissecting atmospheric signatures that orbit alien stars. While we eagerly prepare to analyze these distant worlds, it's important to ponder a question. What about far closer targets? Planets orbiting right beside us, in our very own neighborhood. Chapter 4. Clues closer to home on Europa and Enceladus. On October 14, 2024, NASA's Europa Clipper spacecraft leapt from Earth, starting a demanding journey, a voyage spanning 1.8 billion miles to Jupiter's enigmatic moon Europa. The next hopeful step in our search for life beyond our planet. Years of preparation, hundreds of dedicated scientists and engineers, now boil down to this vast route through the dark between worlds. A careful trajectory lined up through graceful swings past neighbor planets to gain the thrust it needs. The destination, Europa, waits quietly orbiting Jupiter, wrapped in mystery and ice. Europa itself is a ridged and cracked globe, veiled beneath frozen ice, and concealing a remarkable secret below. Imagine standing on this icy shell, scarred by fractures, long, sinuous marks running across a frigid landscape, reaching over 100 kilometers in length. This cracked exterior, flecked with a dull red hue, tells us a story of tension and shifting ice sheets, reflecting the tidal tugs and gravitational pulls of massive Jupiter. Underneath this frozen surface, scientists are nearly certain that Europa holds an ocean of liquid water stretching over the entire globe. Holding more than twice the volume of Earth's oceans combined, it's a deep, salty and dark marine world, cut off from sunlight, heated, instead, by the rhythmic squeezing from Jupiter's immense gravity. Could such an environment foster life? That's exactly what Europa Clipper aims to uncover. Equipped with a suite of state-of-the-art instruments, this remarkable spacecraft will orbit Jupiter and conduct multiple flybys of Europa, skimming just above the icy crust. Each flyby will yield a closer look using advanced radar mapping technology, enabling us to peer beneath Europa's ice, mapping the structure, thickness, and even finding weak points or liquid pockets close to the surface. Clipper won't stop there. It will carefully sample plumes of water vapor as it goes. Plumes which may carry molecules from the hidden ocean beneath. These samples could tell us a great deal about the chemistry happening deep in Europa's inner ocean. Moreover, by carefully measuring magnetic disturbances generated by the salty water ocean, Clipper plans to sound the depth and salinity of that hidden sea. Salty oceans have different electrical properties than fresh water, and scientists can decode this electromagnetic data, painting a remarkably precise picture of conditions below. But Europa isn't alone as an ocean-bearing moon in our solar system. Let's shift our gaze further away from Jupiter now, toward Saturn and its intriguing moon, Enceladus. Recently, the James Webb Space Telescope, JWST, turned its extraordinary eyes toward this small but vibrant moon and made a riveting discovery. JWST detected a plume of water vapor erupting from Enceladus, enormous in scale, stretching 10,000 kilometers into space, spraying out hundreds of kilograms of water every second, eerily unchanged from observations made nearly 2 decades ago by the Cassini spacecraft. The sheer scale is breathtaking, a continuous fountain of icy particles and vapor, soaring outward at astonishing speeds and with remarkable persistence. It's evidence of Enceladus's active geology and evidence of an internal warm ocean far beneath its ice. Cassini's earlier visits to Enceladus told us even more. Not just plumes of water, but also molecules like hydrogen gas, organic compounds. And strikingly, hydrogen cyanide recently identified and reanalyzed Cassini data. Hydrogen cyanide is particularly intriguing. It's a simple organic molecule, but it's also a vital ingredient in reactions leading to complex organic chemistry. This combination of molecules, inorganic, simple organics, and hydrogen, is tantalizing precisely because we know on Earth such chemistry often fuels living processes at places like deep-sea hydrothermal vents. These places, at deep ocean floors, don't depend on sunlight. They depend on the chemical reactions between seawater and rock, a process called serpentinization. Here, on Earth, it supports vibrant ecosystems thriving in absolute darkness. Could something comparable occur on Enceladus, with water and hydrogen gas flowing, and organic molecules feeding possible microbial life forms? It's a compelling idea. Europa and Enceladus both have oceans, and both have energy capable of powering life, but their energy sources differ. Europa's main energy source comes from tidal heating, Jupiter's strong gravitational pull kneading Europa, warming its interior, and probably driving hydrothermal activity beneath the ocean. In contrast, Enceladus's ocean energy might be largely chemical. Serpentinization reactions happening deep beneath its icy shell as liquid water contacts rocks. Serpentinization not only produces hydrogen, it also drives chemical disequilibrium, a difference in chemical potential crucial for life. Knowing exactly how these different energy sources operate helps us understand how life might thrive in these distant ice-covered oceans. Closer to home, our efforts to retrieve Martian samples have faced recent uncertainties, reminding us just how challenging planetary exploration can be. NASA and ESA are striving to return rocks and dirt collected by Perseverance, hoping to analyze them carefully in earthly laboratories for signs of ancient life. Delays remind us that space research is difficult and patient perseverance is essential. Nevertheless, when these precious samples finally arrive, we'll have unprecedented insight into the ancient Martian surface, ancient lake beds specifically, which may preserve fossilized signs of life from when Mars was wetter and warmer. This future promises exciting revelations, strengthening our understanding of how rocky worlds evolve biologically. All these pieces of the puzzle, Europa's and Enceladus's hidden oceans, Mars's ancient lakes, form crucial stepping stones, anchoring our expectations of finding life beyond Earth to concrete, tangible evidence. The precision in these observations, measurements, and sample analyses provides a unique advantage. Reliable, ground truth seeding for models designed to detect biosignatures, chemical signs of life, even on distant exoplanets orbiting stars light years away. By calibrating our tools and expectations using well-understood worlds in our solar system, we sharpen our skills at planetary scale life detection. But even with all this information showing the potential habitability of these ocean worlds, a significant and fascinating question still looms heavily in our minds. How common are civilizations in our galaxy? With ocean moons orbiting huge gas giants, possibly supporting simple life, and rocky worlds like Mars showing signs of ancient habitability, just how many intelligent civilizations might be out there scattered across the stars, wondering about us, just as we wonder about them? Chapter 5. Counting Civilizations and the Road Ahead. In 1961, astronomer Frank Drake scribbled something remarkable onto a dinner napkin. With just a pen and a piece of cloth, he laid down a series of symbols and numbers, a formalized guess at one of humanity's oldest questions. Are we alone in the universe? Now known simply as the Drake equation. It doesn't give us an exact answer, but it does something powerful. It structures the way we think about extraterrestrial life. Drake realized that the number of civilizations in our galaxy that might communicate with us depends on several things, each multiplied together like steps along a staircase. We start with how fast stars form, then move to the fraction of those stars that have planets, the number of those planets that sit in the throne of habitability, the fraction where life emerges, then the probability of intelligent life evolving, and finally, the portion of those civilizations that transmit signals we could detect. But the real kicker, the factor that changes the conversation dramatically, is simply how long such civilizations survive to broadcast their presence. Drake called it L. Today, more than 6 decades later, the Drake equation still sparks debate. With every new discovery, every exoplanet, every refinement in our understanding of the cosmos, we update and rethink it. But recent findings in 2024 offer a sobering revision. Geologists and astrobiologists now highlight the importance of plate tectonics and the proportions between continents and oceans on exoplanets. On Earth, plate tectonics shifts continents around, slowly but persistently, recycling carbon, controlling climate stability, and maintaining the chemical diversity vital for life. But how common could such geological activity be elsewhere? This matters because, without plate tectonics, a planet might lose its livability much faster. The gentle balance we routinely overlook could be rare in the galaxy. Thus, plate tectonics might lower our optimistic estimates for habitability, shrinking the number of potential homes for extraterrestrial life significantly. But worsening the odds even further today, emerges an intriguing new concept. Artificial intelligence, once uncertain sci-fi, has stormed into everyday reality. Its implications affect not only our societies, but also civilizations elsewhere. If civilizations follow a similar path to us and create profoundly powerful AIs, they potentially risk shortening their lifespans drastically. This AI filter might slice civilization lifetimes to mere centuries instead of millennia. Civilizations might arise frequently, develop AI quickly, and vanish before ever transmitting signals long enough or loud enough for us to detect. Suddenly, the term L, lifespan, becomes burdened and fleetingly short. However, not everything is pessimistic in modern SETI. Our techniques have grown impressive. The Allen Telescope Array, ATA, conducts targeted occultation searches, particularly around fascinating star systems like TRAPPIST-1. These occultations happen when one planet slides in front of another from our view. Perfect chances to pick up signals of planetary communication. Precise signals that advanced civilizations might use to communicate internally. In recent ATA observations, scientists captured thousands of candidates, only to find all were terrestrial noise. Yet, it proves the method works, creating a new ray of hope for future detections. Moving further afield, the Murchison Wide Field Array, MWA, pushes SETI beyond our own galaxy for the very first time. The MWA examined more than 2,800 galaxies simultaneously, listening at low-frequency bands around 100 MHz. Though no signals were received during this first attempt, it paints a vivid dream of the possibilities ahead. A future in which scanning entire galaxies for alien signals becomes routine. One enemy of clarity has always been Earth's own cacophony, human radio noise. But there's progress here too. The multi-beam point source scanning strategy addresses this, using multiple telescope beams aimed slightly apart to compare signals in real time. At the 500-meter aperture spherical telescope, FAST, this new system rapidly weeds out Earth-based interference, helping pinpoint genuine extraterrestrial signals should one ever appear. But how do we handle the immense currents of data generated by these telescopes? Petabytes of radio signals every year represent another huge challenge. The solution again arrives from artificial intelligence, but this time as an ally rather than a threat. SETI's powerful AI systems, like convolutional neural networks, now autonomously churn through mountains of data, rapidly identifying meaningful patterns. These AI-driven pipelines learn through deep training, distinguishing what could possibly indicate another civilization from Earth's noisy digital clutter. Self-learning anomaly detectors have also joined the hunt, continuously comparing signals against expectations. Machines teaching themselves to spot what surprises human observers might miss. Of course, as we deploy such robust tools, we encounter a paradox. The heavens remain eerily silent, but the silence itself says little about our actual loneliness. Absence of evidence is not evidence of absence. Our current technological horizons reach only a tiny shallow region of our galaxy, like peering out windows of our home, expecting to see our entire city. Signals dissipate with immense distance, fade into the whispers of the interstellar medium, or simply are blocked by stellar and planetary alignments. Patience, consistency, and ingenuity are critical, overcoming these theoretical and practical boundaries. Looking ahead to the 2030s, new instruments reshape our hopeful gaze. The Habitable Worlds Observatory, planned by NASA, will unlock greater understanding of exoplanets than ever before. We can expect not just more planets, but a finer understanding of their atmospheres. Lunar radio telescopes may rise on the far side of the moon, silent and shielded from Earth's interference, gazing further and deeper into interstellar space. Ambitious programs, like Breakthrough Starshot, hope to send spacecraft, tiny sails speeding towards neighboring stars, returning invaluable close-range observations. Each of these efforts expands human perception even further into space, bringing us closer to distinguishing silence from subtle signals. What if we find nothing? What if, after all our tools probe the sky, after AI tirelessly searches, after we whisper into the black, it remains stubbornly mute? Even a profound silence holds deep meaning. It teaches us the uniqueness of life on our planet. It sharpens the moral responsibility we have towards ourselves, towards life itself. A universe empty of intelligent life, except for one fragile planet, is a humbling thought, yet profound enough to reshape how we view ourselves. It underscores our fragility, the transient beauty of life and intelligence. Yet, each day, we deepen in curiosity. Every spectrum analyzed, every potential beacon checked, every distant world observed brings us incrementally closer, one small step after another, towards answering this eternal question. The challenge stands brilliantly, dauntingly, before us. But so does opportunity. The journey towards certainty shapes not only our science, but also our society itself, an endless loop of learning and wondering. continuously refining our definition of intelligence. So we move forward, driven fundamentally by one incredible question. Each telescope we build, each calculator we program, each experiment we design seeks answers. Meaning, clarity. Drake's equation might forever remain a framework open-ended, with numbers we only imperfectly guess. Yet within those uncertainties, we find our humanity aghast and amazed, awed and humbled, civically and scientifically shaped by searching so long and hard, so persistently, for the ultimate truth. Are we truly alone?